Well, we're switching laptops again. Our next presenter is Hannes, apparently again. But you're representing with Usama, right?
Yes.
Yeah. Okay. So Usama is program, I think, for again the trusted. Repeat that? No.
That's another mic there.
I had it there. The theory open the trusted research department.
Yeah.
That's it, right? Yes, thank you. Working also here at Dresden and George, stay there.
Yeah, no.
You can join here.
Oh, sure. Well, he will.
Yeah, he is supposed to present, right? Yeah, he's here for the first part. That's so Hannes, you're starting.
Yeah.
Your second presentation today. These days.
Yeah. Thank you all for still being here. So as you see from the slide, Usama and I will be tag teaming this presentation. I will start and he will take over. And hope you can also see it on remote. And the talk is about remote attestation, a topic which we covered before in the RIOT Summits. And there's some exciting new development in this from a standards organizations, which Usama will be talking about as well. And I will start with an introduction, and then he will take over. And as you can see, a list from the people, we've been collaborating over several years with many people, and obviously we thank them for all the discussions and all the input. I will start with a motivation of why remote attestation is a useful technology. It's a little bit of a reminder to those who hadn't seen earlier presentations. We then, I then talk briefly about the approach, the solution we came up with. We did a formal analysis as part of this exercise and discovered some vulnerabilities, which is confirmation that formal analysis is really a useful tool in the design process to spot some issues. Of course, then we fix those aspects, those problems, and have a new solution, which then has been brought to the IETF and is being standardized or being considered for standardization right now in a new group. Okay, so what is remote attestation? Many of you may know this famous RC called from the Remote Attestation Working Group, RATS Working Group, which talks about the terminology. It's somewhat unfamiliar terminology in some sense, but it talks, while Johan talked about like classical communication security tasks, remote attestation focuses more on the endpoint, assumes that the communication over the internet is secure or can be secured. Mutual authentication, classical communication security mechanism. But the remote attestation makes sure that the integrity of the endpoint itself can be verified by a remote party. And that's where we use this. That's why also remote attestation, because we want to demonstrate to others that the software and the hardware is indeed not modified and sort of complies to what the golden values are in on the side of the remote party, which we call verifying party, which is a combination of a verifier and the relying party. So it does the verification and the consumption of those values. And all of this works by sending a challenge to this attester. The attester is the device that we want to verify. And in this case, it's in a cloud. A lot of the use cases we focus on are cloud-based use cases, confidential computing use cases. But there are also other use cases where the attester is an IoT device, which is what is probably more interesting to the community here. But it's a generic solution in that sense. So there's a challenge, and the attester then combines a couple of different data, which I will show on the next slide, and then sends that off to the verifying relying party. And then only after then, certain information is released, whether that's some confidential information like AI, machine learning models, or some other secrets. So that's on a very high level, the summary of what you find in this architecture document, IETF RSC. when we look at the trust model here, we see, or we can compare it to the CA model, the certification authority, the classical BKI model, which you see on the right-hand side, which is like introduces these entities, the certification authority, the CA, which issues certificates. And it issues, as shown here below in the box, shows that the certificate is created by having the CA sign the identifier, which is the IDS here, with the private key of the CA. And then, of course, you can generate the whole hierarchy out of this, as you all know from the RFC 5280 specification. But that's what we have on the web servers. It's a classical model. And if we look on the other side, this is the remote attestation model, which is a little different here. We have the hardware manufacturer providing this, sort of serving as the trust anchor, and that manufacturer signs with which or issues the attestation key to the device, which is this item number 1 here. And then when the device is asked to present the remote attestation using the previously shown protocol interaction, it performs a measurement of its environment and then signs that with its private key. So it's on the surface, it looks a little bit similar to the BKI model, but it's a very different context, different trust anchors involved, different procedures. And also the information that is being signed is different. That's why we call that evidence here, the result that is being passed around. And in the CA model, the certificates and its use is well known. But we will see later why both of them actually matter in a complete solution. We have different, well, we are not the first ones to come up with solutions. Obviously, many people came up with solutions, and there are different categories of solutions. At an abstract high level, there's 3 types of categories. There are pre-handshake attestation solutions. There are solutions that focus on the handshake itself, called intra-handshake attestation solution. And then there are solutions that follow after a handshake was established, post-handshake solutions. And obviously all require some changes to the protocols, needless to say, but they differ in terms of the deployment and the application modifications. So they have different pros and cons. That's why over time different solutions were proposed. And if we just plot this on a tree in terms of what solutions, this is not a complete list. This is sort of the more widely known solutions. You see they fall into different categories. Many of them were inspired by the work on confidential computing. So that's why we suddenly have over the last few years significant number of publications on solutions, because confidential computing is a popular topic in the industry. But you also see some solutions that are specific to IoT devices. And we will focus on one solution that we proposed and which was then later analyzed and further refined, which Usama is going to talk about next. That's where I'm going to sit down.
Yeah, thank you very much, Hannes, for the introduction to the topic. And the approach that we have taken, I will start with that one. Namely, basically, we have 2 parts. One is the protocol designer. The other part is the verifier who is doing the actual formal analysis. So the approach in a nutshell is that we both cooperate. Like from a high level perspective, it's the opposite. Like the goal of the verifier is to prove the vulnerabilities in the protocol. The goal of the designer is to show that the protocol is not vulnerable. It's like it works. Only then it will be standardized. But the approach that we have taken is a bit different, namely that we both, verifier and the protocol designers, cooperated in a sense that, okay, we both want the protocol to be standardized, and we want to fix still the vulnerabilities that a large class of attacks are still taken care of. That was the whole idea. And this slide shows the problems or the pain points of the protocol designers, which is that a protocol designer will typically have engineering background, and he cannot really visualize what's the mathematics going on in all of these form methods. From a verifier perspective, it's a whole bunch of systems like Intel SGX, TDX, and confidential computing that Hannes mentioned. So it's a whole system that a verifier actually, even with his mathematical background, he has to learn all of this in order to formalize this. And the idea was that protocol designer in the loop, we take the protocol designers in the loop in order to tackle all of this complexity, such that we can make the protocol verification artifacts more closer to the reality. So it has benefits for both, like protocol designer does not just get a bunch of theorems, he gets some explanations of why this protocol is breaking and how to fix that kind of a protocol. And they get it in the form of pictures, so that I will just skip because of the limited time. So what I want to focus on is that security goals. From the RIOT perspective, what is important is that we also want not only the server side to be supported, but also the client side. And there it's, we believe it's the important or interesting part for this community. That is, the standard TLS properties should continue to hold when we combine attestation with TLS protocol, which means that IoT device should not give over its evidence, which contains private information, including the firmware which is running on that device, over to any server who requests it. So it checks that the server is authenticated and is legitimate, and only then release its evidence. So that's the first part, which is the server authentication. And then, of course, we have to ensure the secrecy of the session keys, namely the TLS session keys, because if these keys are available to the adversary can decrypt all of the data, application data that will be sent over. From remote attestation perspective, we have all the standard goals of remote attestation, namely integrity of evidence, that from the verifying relying party over to the attester, all the claims which are sent over should be integrity protected. They should not be changed by anyone in the network, any adversary, let's say. Then the freshness of the evidence, for instance, the firmware version of RIOT device has been now changed. So it needs to ensure that this is really recently generated and still talking to the same entity, and it's bound to that remote attestation session. The next one is the refresh of evidence. Let's say now it's a long-lived session, that it is monitoring some kind of, let's say, temperature or some kind of sensor, which it is having, and it's a long-lived session. In that case, it also needs to ensure that it can repeatedly track the runtime state of the machine, of that IoT device. So the composition goals are now combining TLS and remote attestation goals, meaning that both are now combined together. How do they link together? So it's not just naively supporting the two goals of the individual sub-protocols, but also tightly bound them together. One of them is that the binding of remote attestation and TLS, which is that each evidence is bound to a specific session of TLS. Note that the freshness property was for a remote attestation session, and this one is for the TLS session. So it's binding remote attestation with TLS. And the second one is evidence that is generated. Evidence is generated by the same server that is authenticated. So it's not a different server. The two are bound together tightly. Then we found some vulnerabilities from this analysis. I will go very quickly over this, which is the first one was the replay attack in interoperable RITLS, which is one of the most widely used protocols in the confidential computing domain, which is that I do one interaction, remote attestation interaction, and with that I get a good status. The adversary records that good state evidence. And when I ask next time, because it's a long-lived session, so things can change. The firmware, let's say, of the device has now changed. The adversary that recorded the old good state evidence, now it replays the same evidence. So the TCP has changed, or it has been compromised. The firmware version, let's say, has been updated, but the verifying relying party never knows that actually it has changed. So it's a vulnerability or a replay attack. Then the second one was remote attestation only in the internet draft, which is that we do only remote attestation. We never check the identity of the machine, which leads to this attack, which is the diversion attack. For instance, this is more from the cloud perspective, that I, as a client, wanted to connect to cloud.example.com. I'm given evidence that it is within the trusted execution environment. Michael talked about trusted execution environments. Now, the thing is that it could be rerouted to, let's say, cloud.random.com instead of cloud.example.com, which I wanted to connect to. The reason being that it never checked identity, it just checked that it has the right measurements. And if the lower one is broken, then it breaks all the security of every trusted execution environment that I have. So that's namely the identity crisis, meaning that even if I have a single machine which is broken, by this I can adversary, the Dolev-Yao adversary, which is a standard formal model which is used, I can divert it to that broken machine, and I can break the security of literally everyone on the network. So what we propose as solution is very simple, namely simple from a conceptual perspective, not to implement, but the idea is we combine both. We take the PKI identity as well as we take remote attestation. Now this provides a very strong guarantee, namely that I check the identity, that it is the one cloud.example.com that I wanted to connect to. And I also check the state of that machine, that it is recently in this specific state, it had this firmware version, it has this, it is connected to this exact hardware and so on, whatever I wanted, I have all these guarantees. The problem being the certificate verify message of TLS is not extensible. And there we propose a number of solutions which required a number of changes. On the left, I have intra handshake attestation proposed solutions. We formally verified two of those solutions. But that was not very attractive for TLS working group because it requires deep changes, as deep as the key schedule itself. So we moved on to the post handshake attestation now, and there the idea is that it uses the exported authenticators RFC 9261, which is that at any point in time, client and server can actually send an authenticator and get back an evidence in the form of an authenticator. So to conclude this part, or the talk itself, the formal analysis was required for standardization, where we started in the TLS working group. It has the FAT analysis. Protocol designer in the loop-based approach is the one which we have used and is novel. Typically, people just develop a whole algorithm and then formally verify it. We used this different from that one. And we found replay and diversion attacks as I presented. And I touched upon this topic that post-handshake is a reliable and better solution in case we have long drift session where we need repeated sessions. For pre and intra, you have to break the session and rebuild the next session whenever you need a newer evidence. And this one is better because then you have the continuity of the application. The current status is that we had a successful BOF, which includes the formal analysis as part of the charter itself. And a long-term vision for us is to the tool ProVerif that we have used for the formal analysis. We develop these formal analysis, we add CryptoVerif, which is doing the crypto verification. And finally, we have a formally verified code in F-star. And the final point is that we have been, as Hannes also mentioned, we have been mainly thinking from the confidential computing perspective in the security goals, as well as all of the work. We would like to hear from this community if there is any other security goal that this community would like to add to the security goals that I mentioned, or if there is any other perspective. Of course, we know like low energy, low RAM, and low ROM are one of the perspectives that this community has. But other than that, from security perspective, if there is anything that needs to be taken care of, because the charter also includes IoT as a tester. So we have some pointers to that. You can have a look at that. And with that, I would like to conclude by thanking all of the co-authors of different works who have contributed to this work, as well as different contributors who have given us feedback in the form of reviews and so on. So thanks a lot. Any questions or thoughts?
In terms of how requirements come from IRTF, does this most handshake solution work just the same for DTLS, or is this tied to DTLS?
Yes, sure. It works exactly the same way for DTLS as TLS. Yeah, because it's really working on top of a different layer, which is namely the attestation layer. This one, for instance, it doesn't care which standard handshake you have. So here you could essentially have a DTLS. It exports the keys over to the
As long as the
application layer.
export, as long as the TLS export is there.
Sure, yeah.
And then if there are no more questions, thank you, Usama, for this interesting talk.